Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, on to lesson 2. In today's lesson, we are going to look at one particular situation where data can be collected. You've got two variables for this situation, and we're going to use that data to come up with a rule to define the situation and use that rule to make predictions about the situation. Okay? So let's go ahead and read through the beginning. In lesson 3.1.1, you wrote rules for patterns found in XY tables. In this lesson, you will focus on using variables to write algebraic rules for patterns in other situations. You will use a graph to predict output for fractional x values. Then you will use a rule to predict the output when the input is too large and does not appear on the graph. So while working today, focus on these questions. How can you write the rule without words? What does the x represent? And for that matter, what does y represent? And then how can you make a prediction? Before we get to that, we're going to do a little bit of a warm-up. And I'm kind of sad that you're not in the classroom to enjoy this game. This is called the silent board game. And what I do is I put up a table of values on the board. And I give you some clues. So here are some random values of x. And there is one rule that fits that will turn the x into the y value. Hold on, I think I have to sneeze. Oh, those were fantastic. I'm sorry you missed them. Okay, so back to business. What we will do is there's a hidden rule here. You're going to do something to the x variable to produce the y variable, okay? And I've given you 3 clues here. And what we would typically do is no one in the classroom would be allowed to talk. Everyone would be looking at the board. And as soon as someone thought they figured out the rule, they would raise their hand quietly, and I would walk up to them and hand them a marker, and they would walk up to the board and they would write in the number for the output. And we would keep going until finally everything was filled in and someone would volunteer for the rule. Now, we can't do that, so I've adjusted the game a little bit for you to play along with me. So the first thing you should do, and maybe I will down the little screen here so that we are only focusing on one at a time and get that screen a nice color. Yes, I like that color. Okay, so what I'm going to do is when I press play, we've got 2 minutes to fill this in and create the rule. And what I'm going to do is every 15 seconds, I'm going to write in another number. And then as you start to figure out what the pattern is, you write down what you think the rule is and you fill in the numbers. Okay, so if you can fill in a number before I put it in, then great. Just be on the lookout to see that when I do put in the number, that your number matches the number that I put in. Okay, because typically what we would do is someone might put in a wrong number because they've got the wrong rule. Someone else in the class could raise their hand, and instead of filling in a new number, they could erase an answer that was up there and change it to what they believe is the correct one. Well, I'm not going to make any mistakes, so we're not going to go through that particular part of the game. Okay, so copy everything down. Go ahead and pause and get this copied down. We'll pause between each one of these, and I have like 5 of them, but I think we'll only do like 2 or 3 of them because of time. Right, we're already 4 minutes into this. All right, so every 15 seconds, I'm going to add in a new number for the output. And if you're not ready, then pause it and get everything set up so that you won't miss a beat, okay? So I'm gonna get ready to go. Oh, actually, let me set up my preferred marker. Dooby-dooby-doo. Okay, we'll do that. Now I'll play. I will, hold on. I will play, there we go. So in 15 seconds, I'm gonna write in the next number. Getting ready for my first number I'm gonna put in. I'm gonna put in -17 here. 15 seconds later, when it gets to the 1:30 mark, I'm going to put in another number. Put in a number 16 here. When we get to the 15-second mark, I'm going to put in the next number. That's going to be the number 4 right here. I could say 2.5 as well. All right, now this is going to be the big one right here. I think this is going to give you the answer once I fill in this one at the, okay, this is going to be 31. And then once we get down to the 30-second mark, you'll have 30 seconds to get to the rule. -3.5. All right, you got 30 seconds. See if you can get the rule in that time. Also pay attention to, once you write down the rule, how many seconds remained, because you can turn this into a little competition. No fair pausing along the way, but well, I can't control that. That's good problem solving on your part. All right, what do we have for our rule? Time is almost up, and the time is up. If you said the rule was y equals 3x plus 1, you would have been correct. Okay, so you triple this number, that's 6, plus 1 is 7. Triple that number, it's -6, and when you add a -6 to a +1, it becomes positive or -5, right? Because you're going to do a subtraction there and keep the sign of a bigger number. And then I thought that one would be the easiest one. You can clearly see 10 gets tripled, and then you add 1 to it. And then you compare that to these, and you're like, oh yeah, absolutely, that's the rule. All right, so 3x plus 1. Let me move this guy down because I'm going to go down a little further. Go ahead and copy down this table. We'll reset it for 2 minutes. Go ahead and pause for however much time it takes for you to get everything in. And then when you're ready, we'll get started. I'll pause myself. All right, so if you're not ready, pause it. If you are ready, I'm going right now. Remember, every 15 seconds, I'm going to put in a new one. This is going to give you a big hint right there. I might do that one next. I think once you see this one, you'll have it. Once again, as soon as you know the rule, you write it down, check out your time, see how long it took you to get that rule. Let's try this one. The last one. It's right here. Okay, 30 seconds before I reveal the rule. Take a look at these. What's happening to each one of those numbers? And I'm going to give you a clue. This one is very helpful. And I think from looking at this one, you might be able to figure out what's going on with the rest of them. Hey, yo. All right, time is up. Here's the reveal. Did you get y is equal to 2x plus 6? That is the rule. All right. So did you get that one a little bit quicker than the previous one? Let's just do one more because we do need to move on to our lesson. Ooh, what's going on with that right there? I think I already know the rule just from looking at that. So pay attention to this guy right there, and let's pay attention to this guy. See if we can figure out what the rule is. Okay, so pause, go ahead and copy everything down. This will be the last one that we work on. Okay, so I'm assuming you got everything filled in. I'm going to get started on this every 15 seconds. Hey, what happened? What did I do? Actually, you know what? We're already at the 10-minute mark. Let's go ahead and just move on to the lesson. We'll be doing more of these silent board games as we go through the unit, so let's just move on. Okay, so this is what the big lesson's about. It's called John's Giant Redwood. This is part one. We'll come back to this in a later chapter. John found the data in the table below about his favorite redwood tree. He wondered if he could use it to predict the height of the tree at other points in time. Consider this as you analyze the data and answer the questions below. Be ready to share and justify your answers with the class. Okay, so take a look at this table right here. Notice this is the number of years after planting. So 3 years after the tree was planted, 4 and 5. And I do want to mention one thing. A lot of times trees are planted, they're not planted as seeds. They're planted as saplings. So a tree will grow a few feet before it's ready to be transplanted and put out in the forest and you know, kind of left to fend for itself. So this would be the number of years after planting, and this is the height of the tree in feet. So I would recommend that everyone write down, we're going to call the number of years after planting our X variable, and the height of the tree will be our Y value. So how tall is the tree? Depends on how many years after planting you measure it. So X is our independent variable here, okay? So let's take a look at the table and answer these questions, okay? How much did the tree grow each year? So from year 3 to year 4, from year 4 to year 5, how much growth is that? And I think you can see that pretty clearly. That is 4 feet. The tree grew 4 feet each year. So with that in mind, how tall was the tree 2 years after it was planted? And how tall was the tree 7 years after it was planted? And how do you know? Go ahead and figure those things out. If you want to set up a table, by the way, to help you with this, we are going to be graphing this information, and you can set up your table this way. Set up the table. Remember, this is going to be your X value. This is going to be your Y value, and you can start with your 0, 1, 2, 3, 4, 5, 6. You might even add a 7th year to that, just because this question was asking about the 7th year. So go ahead and fill in this according to the pattern, and then we'll come back and take a look at the answers. Go ahead and pause and get all those numbers filled in. So how tall, how tall was the tree after 2 years? If it's growing by 4 each year, that would mean that the second year would have to be 13, correct? And year 6 would have to be 29, and year 7 would have to be 33, correct? So just taking a look at this, we know it's growing 4 feet per year. So 13 is 4 less than 17 feet. And of course, the 7 years, you're going to have to add on another 8 to the 5. So how tall was the tree the year that it was planted? Let's go ahead and go to that table right now, and let's just go ahead and fill those numbers in. So we've just filled in that the 2 was 13, and what did we say? The 6 was 29, and the 7 must have been 33. So working in reverse, what's 4 less than 13? That would be 9. And what is 4 less than 9? That would be 5. So this right here represents the year it was planted. Year 0, the year that it was planted in the forest. Okay? So we can come back, answer the last couple of questions. How tall was the tree the year that it was planted? We're saying it would have been 5 feet tall. Now, this is assuming that the tree is growing at the same rate each year. But if you look at the measurements for year 3, year 4, and year 5, it is pretty consistent how it's growing by 4 feet per year. It's not like it grew 5 feet this year and then 3 feet that year. There's a consistent growth there. So we're just going to assume that the tree has been growing consistently and will continue to grow consistently. Now, in real life, this is great for estimations, but shouldn't be considered like an absolute rule to be followed. Although we are going to create a rule, but that rule is for prediction and estimation purposes. It's not expected to be exact every single time. So estimate the height of the tree 50 years after it was planted. How did you make your prediction? Well, how would we go about doing that? I mean, once we figure out what the rule is, we could continue the counting pattern all the way to 50, but can everyone agree that taking this table out to the 50th year, right? We're only at the 5th year here, would be kind of challenging. If it's growing 4 feet per year, can we assume that it's going to be about 200 feet, somewhere in that area? I think so. I might have actually put down the exact answer based on the rule that we're going to find. So let's wait to reveal this until after we go through the rest of it. So resource page 3.1.2b is on the classroom. And once again, you can print it off and you can use it. That's this guy right here. Or you can just create your own graph on your graph paper and create your own table. So does it make sense? Oh, no, we're not there yet. So what we're going to do is we're going to take all of these points where this part of our table represents the number of years, which is our x-axis, and this represents the height, and I believe they said that that height was in feet, correct? So let's go ahead and take all of this data and let's plot it on the graph. Go ahead and pause the video as you insert all of these ordered pairs. Remember, these are XY coordinates. So like the first one would be 0, 5. Then the next one would be 1, 9, and so on and so forth. And it doesn't look like we're going to have room for the 7th one. So we're just going to stop at 6. Okay. You go ahead and graph all those points on the table. And I'll do the same. And when I unpause and you unpause, we'll have the graph here. Okay, let's take a look at the graph. So we're going to plot 0, 5, 1, 9, 2, 13, 3, 17, 4, 21. Let's get that right in the middle there. 21. 5, 25, and then 6 would have been 29, which is just getting off the graph, so maybe we don't plot that one, but let's go ahead and plot it anyway. There's space right there. You can kind of get an idea where that should go. You notice about the graph? Forms a straight line, right? Now, I want to show you something about graphs. One of the reasons why it's so important to graph multiple points, not just 2 or 3 of them, is sometimes you get points in the wrong spot, like this guy right there. And you look, and we're expecting it because there's a constant growth rate. We're expecting this to, stop it. We're expecting it to be a straight line, right? And so when you have 5 or 6 points that are all on the straight line, but there's one of them that is off, you can kind of tell which one is in the wrong location, right? So it's like, oh, yes, that's right. This is 5, 17. That was 5 1/2, 17. So we just placed it in the wrong location. I'm going to clean this up a little bit. And so it does form a straight line, but the question now is, should we connect the dots? Is it okay to connect the dots? We've got this idea. There's 2 different types of graphs that we can have here. One where we connect the dots and one where we don't. So what do you think about this? Does it make sense to connect those points? Now, let's explain what the graph is telling us. The x-axis represents the time in years. Every one of these lines represents half of a year. But couldn't we measure the tree at any point along this continuum? We could measure the height of the tree after 9 months, which would be 3/4 of a year, and see what its predicted height would be. So doesn't it seem like we should probably have a line there, since any one of these dates we could measure the tree and it should fall on that line? So this is an example right here of a discrete graph, but I think we need a continuous graph. So it wouldn't make sense. It does make sense to connect the points because you can measure the tree at any time. So what I'm going to do, and what I would suggest you do, is go ahead and take your straight edge, get a ruler, and go ahead and put that line in there. Let me go ahead and start it. Now I'm going to do that. I'm going to do this. That's what I'm going to do. Okay, there's our line, and it goes on forever because the tree will grow the 7th and 8th, the 10th. It'll keep growing for years and years and years. So that's where we put the arrow at the end of this to suggest it's going to keep on going. Time is not going to stop, and therefore the tree will not really stop growing until the day that it dies. So the next question asks us, can you use your, no, according to the graph, what was the height of the tree at 1.5 years after it was planted? Well, that was not one of the data points in our table. However, this is one of the nice things about having a graph, is I can go to the 1.5 year point and take it up to the graph, and then I can figure out, okay, what would that point be on my y-axis? And so this point here is 1.5 is my value for x. What does it look like as my value for y? That would be 8, 9, 10. Looks like it's going to be 11. And so based on the graph, because we put this data into the graph, we can predict that the tree would have been 11 feet tall after 1.5 years. Now, here's a good question. Can you use the graph to predict height after 20 years? Does our graph give us that ability? No, it doesn't, because our graph, I mean, you could make a graph that goes out to 20 years. You could make a graph that goes out to 50 years. But this particular would be a big graph, right? And this one only takes us up to the year 6.5. So this is not an ideal situation for graphing that far ahead. So we would want to come up with another strategy. So no, we cannot predict after 20 years, much less 50 years, because the graph doesn't go up that high. So John is not satisfied. He wants to be able to predict the height of the tree at any time after it was planted. So what have we done so far? We have found the table and we've entered in those. Now we're going to play a silent board game, and we're going to create an algebraic rule for this data and then use that rule to try and figure out the 50th year how tall the tree will be. So can you figure out what the rule is by looking at this information? What do you do to the number 1 to turn it into the number 9? What did you do to the number 2 to turn it into the number 13? I think this is a good one right here. Take a look at that. What are you doing to the number 4 to make it 21? It looks like you're multiplying it times 5 and then adding 1, correct? This one, you would just multiply times 5 without adding 1. So it's got to be a consistent rule that works for all of them, okay? So it looks like, what's going on here? This was pretty important. If x is equal to 0, then it really doesn't matter what number is being multiplied times the x. You're still going to get that 5. So what does that tell you about the number that's being added on at the end? That's a big clue for you. That number that's being added on is a 5, right? So let's go back and look at all of these. What appears to be the rule? What do you multiply times 1 and then add 5 to it get the 9? What do you multiply times 2 and then add the 5 to it to get 13, and so on and so forth? If you said y is equal to 4x plus 5, then you would be correct. Because look at the third year. 4 times 3 is 12, and 12 plus 5 is 17. 4 times 4 is 16, plus 5 is 21, and 4 times 5 is 20, plus 5 is 25. So now let's go ahead and let's figure out what is the height of the tree going to be after the 50th year. You have that answer already? Remember when we made the prediction? Since it was growing by 4 feet per year, you figured it would be somewhere in the 200 range. And that's exactly right. The multiplier was 4, because that's how much it grew per year. So 4 times x plus 5 gives us an answer of 205. So it's going to be 205 feet in 500 years. No, 50 years. 50 years. So that's it for today's lesson. What did we do for time? Well, we did okay, a little over 25 minutes, not too bad. Okay, so you are bound to have tables and graphs showing up in your homework. Make sure you copy those down, make sure you complete the information, and you're most likely going to be playing kind of like a silent board game to try and figure out what the rules are for the tables and for the graphs. I'm not sure that tonight's homework is going to have that, but you're going to have that quite a bit in the future. And eventually what we want you to be able to do is take any rule and create a table and a graph from it. Take any graph, take that information from the graph and put it into a table and make a rule for it, or be able to take your table and create the graph and the rule. We want to be able to get any one of these 3 representations and create the other 2 from the first one. Okay, so the way you get there is by practice, practice, practice. So make sure you're doing your homework and you're showing your work, and make sure you're making your corrections if you made a mistake. All right, take care. Bye.
Hey, feeling good, like I should.